Hello, everyone. Thank you for joining us on this track to discuss overarching properties. My name is Jim Chelini, and I'm the chair of the Overarching Properties Working Group. So the FAA initiative started in 2015. It formed a working group of industry, academia, and certification authorities. And the idea was to define a set of meta objectives or overarching properties intended to allow an applicant to receive approval through demonstration of the possession of these properties. The initial plan was to provide an advisory circular. However, the current plan is undefined and will be determined after we finish our mission. The Overarching Properties Working Group, as I said, has participants from industry, academia, and the certification authorities. At the same time, a European research group, RESSAC, the Reengineering and Streamlining Standards for Avionics Certification, was also experimenting with ways to streamline the process. They work cooperatively with the Overarching Properties Working Group, or OPWG. They were members of that. They completed their mission in 2018. We have taken the recommendations from their activities into account into what we're doing now. We have also published the first of several white papers on the definition of overarching properties. That was published in 2019. And that paper is available at both the NASA and FAA websites shown on the slides. The purpose of overarching properties is to demonstrate that a system is fit for use through possession of these properties. As an example, compliance with DO 178C is a way to show this, but is not the only one. And what we're looking to do through the overarching properties is broaden the means of compliance. So the overarching properties at the highest level are three properties. Intent, the defined intended behavior is correct and complete with respect to the desired behavior. Correctness, the implementation is correct with respect to its defined intended behavior under foreseeable operating conditions. And Innocuity, any part of the implementation that is not required by the defined intended behavior is shown to have no unacceptable impact. So basically, we understand what the system must do. We demonstrate that it's correct in its performance of that, and that if there's additional functionality, it does no harm. Our initial approach, based on our experience with 178, was to follow a process-based evaluation criteria. And RESSAC actually experimented with applying this evaluation criteria to their products. They found in some areas the criteria was too prescriptive, and in other areas too vague and subject to misinterpretation. So they identified a need to determine if a product possessed the properties through some other means. A series of workshops were held with the RESSAC team and OPWG and CERT authorities, and quickly came to focus on the use of assurance cases or structured arguments as a way to demonstrate the possession of overarching properties. So an assurance case is an argument with its supporting artifacts. In the context of the overarching properties, the assurance case is intended to show how the properties are possessed by an item or a combination of items, essentially a system or subsystem. It is intended to also work for software, hardware, or at the system level. The argument introduces, summarizes, and provides the context and justification for evidence of the possession of the properties. When we talk of evidence, this is reference to a means of assessing the truth for a given premise and the artifacts that are created or examined in that assessment. So an argument contains that were supported by evidence. In the following talks, they will describe the construction and assessment of arguments and provide insights from 2 current projects that are using structured arguments to demonstrate the possession of the overarching properties. The next talk will be on the construction and review of OP-related arguments by Michael Holloway of NASA. Zamira Daw from Raytheon will present the Utopia Project, and Tony Aiello of AdaCore will present QGen, a code generator. Thank you again, and enjoy the session. The updates of where we are is the current working on a white paper for constructing the assessing overarching properties. This is what Michael Holloway will focus on. That's currently in internal review. We will hold a plenary June 17th to review comments on that paper. The goal is a release of this white paper by September. Once again, thank you for your time and enjoy the following sessions.
Hello, I'm Michael Holloway and a senior researcher at NASA Langley Research Center in Hampton, Virginia. I want to thank you for taking the time to watch the Overarching Properties session. Now that Jim has discussed some of the history behind the OP work, I will provide a very rapid introduction to some foundational terms and concepts we are using for talking about the OP-related arguments. But first, 2 disclaimers. As a matter of long-standing practice, I use slides as visual aids only. My slides are always incomplete without my spoken words. Second, nothing I say is an official position of NASA, as I'm sure you already know. So now on to the substance of my talk, which again, I will go through very quickly to allow more time for the case studies. If you don't already have your own copy of Understanding the Overarching Properties, you can get it at this URL or by searching for it at ntrs.nasa.gov. I'm going to show you now the full text of the OP description, not for long enough for many of you to read it, but simply to emphasize 2 very important points, which are not always understood by folks. The first critical point is that the parts with a gray background, the statements and definitions, constitute the complete definition of the OPs. The section in the white columns, requisites, assumptions, and constraints, are about matters concerning the process of showing an entity possesses the OPs. They are not about and do not affect the meaning of the OPs themselves. Second, the labels, intent, correctness, innocuity, are just that, labels. They carry no more meaning than if we'd called them Ashley, Bobby, and Charlie, which is why they also have a white background on this slide. Now on to the vocabulary. And similar to the previous slide about the OPs, here's where you can obtain a primer on argument OP edition, or again, you can simply search for it. The purpose of that document was, well, and still is, to establish for the OPWG a common understanding of terms, concepts, principles, and uses of argument. Now, viewers who know something about the assurance/safety case work of the last couple of decades are going to see some differences between our terms and those often used in that community. These differences stem from our strong emphasis on harmony with the mature principles of argument, which have been honed over thousands of years. Unfortunately, at least in my view, seeking such harmony has not always been the case within the case community. So that's why you'll see some differences. I myself was once guilty of plunging forward without carefully taking into account the long and rich history of argument. But the vocabulary in the primer shows the extent of my repentance from my past terminological sins. By argument, we mean an attempt to convince others to believe that is, accept as true, a conclusion through reasoning from one or more premises. Thus, the conclusion is the statement you want your audience to accept as true. In the context of OP-related arguments, the audience will likely include folks in the development team and from or representing approval authorities. A premise is a statement you think your audience either already believes or will come to believe after further argument. And reasoning is an explanation of why you think the premises should cause your audience to accept your conclusion. In most traditional expositions of argument, reasoning is often not stated separately, but simply included among the premises. But based on reasoning, I somewhat ironically don't have time to discuss. We think calling it out explicitly is worthwhile in general, and especially worthwhile for OP-related arguments. Finally, we use the term binding to refer to an association between a term used in an argument and the real-world information to which that term refers. You think of definitions, for example, or links to specific documents or to development artifacts. We also find it useful to distinguish between atomic arguments and compound arguments, as shown here. An atomic argument consists of a single conclusion together with its immediate reasoning, premises, and bindings. And rather obviously, I suppose, a compound argument refers to an argument consisting of at least two atomic arguments. And finally, for the purposes of this rapid introduction, the primer itself includes some additional terms that we're skipping here. We call an argument cogent if it is a good one. That is, if it rationally justifies believing its conclusion to whatever level of confidence is needed for the application. In the context of OPs, whatever level of confidence is needed for showing possession of the OPs. Now, the level of confidence is, of course, as I'm sure everyone recognizes, a complicated concept, which I'm not going to address here, but we do address as part of a separate, not yet published paper. So that's a bit about our vocabulary. Now on to a bit about notation. Here's where you can find the definition of the friendly argument notation, or FAN. It directly instantiates the vocabulary, as this document that you can get here will show. Here's an example of an atomic argument concerning possession of the intent OP by a subsystem abbreviated as MDSS, as it might be written in FAN. I'm not going to spend any time on this example because you'll see more complex examples of FAN in the next presentation about the Utopia project. The last topic I want to quickly address before yielding my time is an approach to argument assessment, which we've just finished a draft paper describing. We call the approach the eye test for reasons I'll leave to the viewers to discern. At the heart of the eye test for assessing a compound argument, which all OP-related arguments will surely be, are these three steps. Isolate an atomic argument, pick one, interrogate it, that is, assess its cogency, then iterate, repeat the process until all atomic arguments are assessed. Let's expand a little bit on this. Here you see the interrogate step expanded and a fourth unlabeled integrate step to be done after all the iterations are done. So to interrogate the cogency of an atomic argument, we propose asking a collection of questions. You see the four highest level questions here. Is the syntax proper? Are the premises acceptable? Is the reasoning acceptable? Is saying yes to the conclusion justified? Thus, if you use our approach, you can say a cogent argument is also a spry one. Each of these high-level questions is further expanded into more specific questions, such as, is each premise believable? Does a binding exist for each term or phrase used in the argument that doesn't have a well-known unambiguous definition? Is the reasoning consistent with current knowledge? And more. You can also see on the slide questions to ask during a final integration pass over an entire compound argument. Are the bindings consistent? Are the conclusions consistent? Does every path through the argument terminate with premises that are to be believed, that are believable? That concludes my rapid introduction to the foundations of OP-related arguments. Thank you for watching. I hope you will find the remaining talks in this session interesting and informative.
Hello, my name is Zamira Daw, and I work at Raytheon Technologies Research Center. And today I will present an industrial case study that shows how to use overarching properties. This project has been funded by NASA, and I work together with my colleague, Scott Beecher and Pratt & Whitney. So first, let's talk why we wanted to use overarching properties or OPs in the industry. So currently certification and standards ensure a very high quality of the software in aerospace. However, the standards do not always support incoming technologies like AI, and that is something very important in the industry currently. So we believe that overarching properties can help to certify systems where currently standards are not applicable or require extra resources that do not add additional safety assurance. The specimen of this industrial case study is an UAV, an unmanned aerial vehicle that has collision avoidance algorithm. So this algorithm uses an onboard model that predicts the dynamic behavior of the robot. We propose to use a hybrid approach that combine existing standards with OP. And here, as you can see, we're using a DO178 for the controlled part of the UAV, the sensors processing, and so on, the other software components, except for the onboard model, where actually we use OPs. So current standards require to have a requirement traceability from the high-level requirement to the functions, to the mathematical function on this model. But this traceability do not increase the safety of the assurance, specifically in this case. And therefore is what we want to use OPs to propose an alternative methods for mean of compliance for the onboard model that reduce the amount of effort required for do this and requirement traceability, but it still guarantees a high safety assurance. So before we go into the details of the argument, I wanted to show how we see these OPs fitting with the current certification process. So during the planning phase, the certification argument is developed by the applicant. And during this phase, we see that here on the right, what we call a certification argument. So the certification argument is composed by the detailed argument that are an argument that is provided using FAN. Michael Holloway explained it before. The binding document that provides background information that will help the evaluator to understand the systems, what you are really proposing on the high level, and then the argument on the graphical representation that provides an overview of your argument. And the idea is try to understand what is the high level picture of your argument. So now, while you are doing that as an applicant on the planning phase, there will be a moment when you are done and then you wanted to go to the certification authorities. At that moment, you will take a snapshot and tie it to the PSAC. And the idea is we call it then the PCA, the Plan Certification Argument. So here the certification authorities will evaluate that argument, provide either an approval if they agree the argument is sufficient, or they wanted to rebuttal. So meaning thinking that the argument is not sufficient, or there is evidence missing that you are not providing, or maybe the argument is not really, you cannot understand what you are trying to propose. So that is the reason that we have here arrow, because it's one to say, and that is an iterative process between the applicant and the certification authorities. So once the PCA is approved, so then the execution phases start. And that is really when the system is developed. And during the development process of the system or the execution phase, so we envision that we will create a lot of evidence that support this argument, that almost the leaves of the argument. And but there might be also be changes on the argument itself. However, we envision that these changes are minor. And if there really are bigger changes on the argument, that you will need to go back to the certification approval for have a new approved PCA. So now, once the execution phase is done, again, you will take a snapshot from the argument and tie it together with the SAS. And that argument we call the AAS, that is the argument accomplishment summary. So due to timing limitations, I will only explain two top-level arguments, the one from intent and the one in Innocuity. So let's start here with intent. Here, what you can see, so on this side, so on the left, you will see the conclusions, justification, and the premises of the argument. And on the right, you actually can see the bindings. And here is actually when you can find the definition of underlined words that you have in the argument. So the conclusion of this argument is that the onboard mole holds the intent, and we use the definition in that the is provided by the OOPs. However, we customize that definition, how you see here on the right, in which actually we define what is the defined and intended behavior, that for this specific application, there is the requirements of the onboard mole, the desired behavior, what the stakeholders want. And in our case, since we're talking about a software component, the stakeholders will be the system group. And they define as a desired behavior that the onboard model have to model the robot's dynamic at a level of the accuracy as needed by the control. And that is very important, especially the last part, because it's telling us that they require a model that describes the behavior of the UAV. However, it has to be accurate, but not as only as needed as by the control, and not the super highly accurate. So now the question is, what does it mean correct and complete for this specific situation? So here in the bindings, we define what is correct and complete. And we define it that the requirements are complete if they capture the robot's dynamic, the accuracy, robustness, memory, and timing aspects. And now we also see that the requirements will be correct if we can actually show that there is a functional equivalence between the onboard mole and the robot dynamics. So now if we look at the first premise that we have here, so the first premise states that the offboard model is a highly accurate representation of the robot dynamics. So here the offboard model is a non-flight software that is used for development and an analysis of the UAV. So the offboard model in relation to the robot dynamic is very close. However, we cannot use that in an onboard platform because of restrictions on processing time and also on resources. So that is the reason why we really required this onboard mode. So, but since we have this offboard mode that is very highly accurate in relation to the robot dynamics, we can use it to calculate the accuracy of the onboard model. And how here is defined in the bindings, the accuracy is represented by the difference on the outputs of the onboard mode and the offboard mode. So here, if we look at the premise number 2, the premise number 2 guarantees that the accuracy of the onboard mode in relation to the robot dynamics, it's okay and is enough for the robot, for the control. But we use it, or have we see in the premise, we are using the off-board mode for doing these calculations. So now if we look at the premise number 3, so here that premise states that onboard modes robustness requirements are correct and complete if they cover of nominal values, also numerical instability. And this numerical instability shown here on the right, it's caused because of the discrete mathematical abstraction using in the mod. So that is the reason why we need to describe it there in the requirements. So now if you look at the premise number 4, that states that the memory and timing constraints provided by the target platform that we're using needs to be also addressed in the intended behavior. So as you can see in the definition of the correct and complete that we have here in the justification, that is showing that we need to show the robot dynamics, accuracy, robustness, memory, and also functional equivalence on the robot dynamics. We can see that these 4 premises that we're showing here are sufficient to hold intent. But maybe before, but something that is good to keep in mind is that all these premises will have OR support, either supported by an OR argument or also will be supported by additional evidence. And I will talk about that later in the presentation. So in intent, we focus on defining our intended behavior. So now in Innocuity is a little different because we're focusing on identify the behaviors in the implementation that are not defined in the intended behavior. And also to show that these additional behaviors do not have an unacceptable impact. So something that I want to mention maybe before we start to go into the details of the argument is that here on the right, so is that additional requirements added during the development process, like what we call derived requirements, are expected to be on the defined intended behavior. So that is the reason why we don't address here in Innocuity. So another thing that I also want to mention is the thought process in Innocuity is very different than the thought process that you use for intent and correctness. So in Innocuity, you actually need to think about all the possible causes of additional behaviors in that implementation. And that is the reason when we started writing Innocuity, we started to work on defeaters. So what will defeat our argument? And then later on in the argumentation process, we transform that defeaters into the premises. And here you will see then the premises here. So here, these 4 premises that you're seeing right now aims to identify additional behaviors. So the first premise, identify open problems that consist in unfinished features that are not releases for a specific product version. And of course, that will lead that the implementation that we have there doesn't match with the requirements, since a given requirement has not been fully implemented yet. And that happens quite often in the industry. So therefore, it's very important that we pointed that out here in Innocuity, because we need to understand if that open problems or unfinished features will affect maybe the safety, will have any impact on the safety of the system. So now premise number 2 and 3 address the implementation choices. So in our case, there are different ways to implement onboard models. So for example, networks or looking up table and so on. So each of the implementation choices will bring their own possible additional behaviors. So in our case, we use basic algorithm approximation. And for that specific implementation choice, there are unintended behaviors that occurs because of the discretization of the calculations and also by constrained memory and processing time. And as you can see in premise number 2, we address that in unintended behaviors in intent. So in the requirements that address accuracy and robustness. So, however, we wanted to mention that here in the argument for Innocuity to facilitate the understanding of the argument, but also to show that we don't have any gaps in our analysis. So therefore, it was important that we show it here. So these will be the behaviors that we are expecting to see. They are not inside of the final intended behavior. However, they will still have our additional unexpected behaviors. And for that, we are proposing here with the premise number 3 that we will use system regression testing and robust testing to address or identify those behaviors. So now, premise number 6 aims to list the set of software functionalities or technologies that are known to add unintended behaviors, like machine learning, multi-core, multitasking codes, and so on. So in this premise, we are just, in the premise number 6, we're just stating that we are not using the onboard model implementation doesn't use these common or software functionalities and technologies. So this premise is really not required in this argument. However, we put it there because we wanted to answer possible questions of the evaluators beforehand, so that they will not come and tell us, oh yeah, but you didn't saw unintended behaviors of non-determinism function. And it's, oh, we didn't do it because we actually don't have it. So before having that question from the evaluators, we wanted to have it here in the argument. So now premise number 4 and 5 ensure that the impact of the additional behaviors is acceptable based on a safety assessment. So summarizing this argument, so the argument shows that the onboard model holds the Innocuity by first identifying possible additional behaviors of the implementation, also propose a system regression testing and robustness testing to uncover unknown behaviors, and also have an safety assessment for the found additional behaviors. So here in these slides, we are showing the entire argument, the one that we actually tie to the SAS, and that will be the argument accomplishment summary. And here we discuss the part of intent and Innocuity, as you can see here. But we can see that the premises that I show in previous slide here are tied to different arguments. So meaning they will have additional arguments that support that premises in intent. However, in Innocuity, we actually have evidences. So the evidence are the leaves of this argument. So here, the part that I am showing now, the part of the correctness. So these are the argument that will show that the onboard model holds correctness by verifying robustness, accuracy, and also memory and timing constraints. And what is actually very matching with the defined and intended behavior that we show in the intent slide. So the argument that you see here on the red box, they are the portion of the argument that might be added during the execution phase. So that means that this argument that you see here is almost the planning argument, except for the 3 premises that you see on the box. So that is, I just wanted to show maybe how little it will change after the execution phase. And also maybe it can be that while you were doing the planning, you thought, okay, it will be an evidence that will tell me how the implementation satisfy the time requirements. But while you're doing the implementation, you saw, oh, actually, I need to add more explanation to it. And maybe the best idea is to add it using an argument itself. So here's something that also I wanted to point out. So this evidence that you see on the leaves can be supported by one artifact or by multiple artifacts. So for example, in the safety assessment evidences, maybe I will have an artifact that show the process that you are doing and another artifact to show the results. So it can be multiple argument if needed to verify or to satisfy that premises. So as a summary, here are important takeaways that I want to leave you with after this presentation. So OPs can provide a flexible and efficient approach that is still guarantee the safety of the system. And we propose a hybrid approach using overarching properties for a specific part of the system, and the rest of the system is certified using existing standards. So we think that the hybrid approach will be the common approach to use, because on one hand, you are leveraging existing standards. They also provide very good guidelines. But on the other hand, you take these parts where the standard doesn't support your technology, and then for that one, you will propose a new argument, a new way to do it. So in our experience on this project, we have a team for 2 members, and we think that combination was quite successful. So in one hand, we will have one team member that was the domain expert. In our case was Scott Beecher from Pratt & Whitney. He's an expert on this type of systems and also in the certification part. Now, on the other hand, we have an argumentation expert that is in this case is me. And here, what we saw is the domain expert will provide which are the evidence that are required to satisfy something, but is the argumentation expert the one that really try to understand if the argument is complete, if it's not ambiguous, and all the parts that needs to be are required to write an argument. So these industrial examples show how OPs can be used in a realistic settings with realistic artifacts in a realistic system. And also, if you are more interested in the entire argument of the onboard model, we are presenting in the coming DAX conference the whole argument. And so you can find it in the IEEE libraries, the paper after September. So this example only use OPs for a software component. And what it actually was nice, because then you can actually see very well how to use it. However, we are currently working on another industrial example that combines systems, software, and safety aspects in an argument. And we think that also is a nice property of the OPs, because you can combine different aspects into the same argument. And I think that's pretty much for my presentation, and I'm happy to answer any questions in the chat.
I'm Tony Aiello, and I'm going to be talking about the TQL1 qualification at QGen using the overarching properties. QGen is AdaCore's qualifiable code generator for Simulink and Stateflow. QGen targets a large number of Simulink blocks and covers a large subset of the Stateflow language. Using QGen, we can generate C code and we can generate Ada. For TQL1 qualification of QGen, we're targeting MATLAB 2018B, and we're generating MISRA C. Qualified tools are interesting because certifying software to DO-178 is expensive, especially for level A. There are many required reviews and verification objectives that focus on source code, including testing of the source code using low-level requirements and MCDC coverage of the source code. Through DO-331, which covers model-based development, there's a promise of significant cost savings. But these cost savings are only fully realizable if the code generator that's used from the model is qualified to TQL1, which is the highest level of qualification. With the TQL1 code generator, the low-level requirements, which are expressed as a model, are generated into source code automatically. Now, what's important about TQL1 qualification is that applicants using a TQL1 qualified tool can take credit for certain certification objectives. So for QGen, we cover many objectives, and 3 of the most important are shown here. Applicants can take credit for reviewing the generated source code without actually conducting this review, because the TQL1 qualification of QGen guarantees compliance with the requirements and coding standards. Likewise, testing of the generated source code is unnecessary because TQL1 guarantees conformance to the Simulink semantics. Finally, applicants can take credit for coverage analysis of the generated source code because TQL1 for QGen guarantees that model level coverage will imply code level coverage. So these are the kind of benefits of having a tool that's been qualified to TQL1. Now, traditionally, to qualify a tool to TQL1, a tool qualification applicant would use DO330, the tool qualification supplement. But DO330 is closely tied to DO178, which itself is meant for airborne software certification. And so at AdaCore, we wanted to seek a new qualification approach. When we looked at DO330, we saw that DO330 requires substantially similar objectives to those required by DO178. And we felt at AdaCore like this approach was particularly awkward for tools. There are 3 key reasons for this. So first, the hazards for tools are very different from the hazards that you see for airborne software. For airborne software, for example, it's generally completely unacceptable for the software to halt and fail to produce any output. For a tool, on the other hand, if the tool detects that there's some problem and halts, this is not an issue for the user of the tool. It's an annoyance, and it undercuts the business case for the tool, but it doesn't undercut the safety of the use of the tool in a qualified process. Secondly, tools are fundamentally COTS, whereas airborne software is frequently bespoke. Tools are built to address multiple and heterogeneous use cases. For QGen, for example, we want to be able to support multiple different programs who use QGen to develop safety-critical software. We also want to be able to support non-qualified uses of QGen, wherein we may support more blocks or more modes in the usage of the tool. Finally, and perhaps most importantly, tools must evolve to a level and at a pace that's different from that of airborne software. And we must be able to requalify the tool to support that evolution. As an example, when newer versions of Simulink come out, we would want QGen to be able to target those newer versions of Simulink. Similarly, if we find an issue in QGen, we would want to be able to fix that issue so that the users of the tool don't have to continue to work around it. With all that being said, AdaCore wanted very much for any new approach that we follow to allow the use of the qualified tool to not have to follow an alternative means of compliance. That is, we want applicants who use QGen to still be able to follow traditional DO331-based processes. So the approach that AdaCore selected for the qualification of QGen is to demonstrate possession of the overarching properties using an assurance case. Now, Jim already provided this definition of assurance case, which comes from RESSAC, but I'll go through it again because I feel like it's a good definition and it's important. An assurance case is an argument with all of its supporting artifacts. The role of the argument is to introduce, summarize, and provide context and justification for the evidence of possession of the properties. And evidence is tied to the artifacts that support the argument. So, for the qualification of QGen, AdaCore is demonstrating overarching properties using an assurance case. And this assurance case allows us to propose the evidence that we think will be sufficient to support the tool, to provide the rationale for the sufficiency of that evidence, and then to provide the evidence once it has all been developed. The argument then is the means by which we justify TQL1 qualification of QGen. In our development of the assurance case for QGen, we start with a structured argument. So our argument is built using the modified Toolman form that was inspired by the recommendations of RESSAC. This is similar to what Zamira presented and similar to the friendly argument notation that Michael presented, but it has some minor terminological differences. So at the top of each of our atomic arguments, we have a conclusion. The conclusion is what we want to derive from that atomic argument. We have reasonings. These support how the conclusion may be derived from the given premises. We optionally have backings, which support our reasoning. And then we have the premises, which provide the grounds for the atomic argument. These may be references to evidence. These may be conclusions from another atomic argument, or these may be explicitly identified assumptions upon which the argument rests. Finally, we have optional defeaters, which enable us to record challenges to the soundness of the atomic argument or the truth of a conclusion. We can then rebut the defeater using another atomic argument. We provide two views for the structured argument of QGen. The first view is a textual view, which again is very similar to the friendly argument notation that Michael and Zamira showed. Here, we've organized the elements of the structured argument in a way that we think makes it easy to read and easy to see the role that each one of these elements plays in supporting the structure. For our premises, we explicitly identify if the premise is the conclusion of another atomic argument, if the premise is a reference to evidence, or if the premise is an assumption, not shown on this slide. We also provide a tree-like view of the argument. In this view, each leaf node at the base of the tree is a single premise, and that premise is either an assumption or a reference to evidence. Each interior node of the tree is a complete atomic argument. So much like the friendly argument notation, you can zoom in on the interior nodes of this tree, and you can read the complete atomic argument right there on the tree. We feel like the tree view is helpful because it allows reviewers of the arguments to better understand the relationships amongst the different atomic arguments, particularly to understand sibling relationships, which can be difficult to see in a linear flow of text. So that's a summary of the approach that we're taking in QGen and the mechanics of how we're presenting the arguments. Now I'd like to pivot to a brief discussion of the content in QGen and how we're adapting the use of the overarching properties for the qualification of QGen. The QGen structured argument starts with an atomic argument that says we will make a compelling demonstration for the qualification of QGen. This is supported by two arguments, an argument on the right, which gets to the confidence in the demonstration, and I'll talk more about that in a moment, and an argument to the left, which asserts the fitness for use of QGen in a qualified approach. The fitness for use argument is supported by a possession of the overarching properties and a risk assessment. I'll also talk about the risk assessment in a moment. For the possession of the overarching properties, our approach is essentially the same approach that Michael and Zamira talked about. So first, we talk about the intent of QGen. And in this part of the argument, we focus on our requirements, the validation of the requirements, and our assertion that the requirements are complete. Then we talk about the correctness of the implementation. Here, we look at how we've implemented QGen, and we show that the implementation of QGen satisfies its requirements. Finally, in Innocuity, we look again at the implementation of QGen, and we ask if there's any part of that implementation which is not directly traceable to the requirements. If that happens, we justify that part of the implementation and show that it is safe given the expected use of QGen. So that's our approach to showing possession of the overarching properties. Let's talk about the risk assessment. The overarching properties were originally intended for the development of an item or multiple items in the development of a system like an aircraft. And there, because of this assumed system context, the overarching properties assume the existence of a safety assessment that would be conducted at the system level. For a tool, this assumption doesn't really make sense, and arguably it doesn't hold. There is no real system level if you consider QGen and its qualification. At best, there is the specific role of QGen in a given development process that is seeking certification of the software it will produce. So what we do is we introduce an explicit risk assessment to support our use of the overarching properties. In essence, this risk assessment stands in for the missing safety assessment that was originally assumed by the overarching properties. There are two pieces to the risk assessment that we're conducting for QGen. The first piece focuses on tool use hazards. These are the hazards that might arise in the use of the tool as part of a safety critical software development process. Here, we elicit these hazards using a HAZOP that's conducted over a functional decomposition of QGen. The second category of hazards are tool development hazards. These can be seen as potential defeaters for the correctness of QGen, and they ask if there's specific ways in which we've implemented QGen that themselves might lead to additional hazards. So for example, in the development of QGen, we've used object-oriented programming. So we've considered DO 332, and we ask if there's details of object orientation that might pose a hazard for QGen's ultimate safety. We also consider the common weakness enumeration from MITRE and look to see if any of those previously identified patterns might pose some sort of a risk for QGen. Once complete, we use the risk assessment as the basis to drive safety requirements for QGen. These feed into the intent part of the argument. We also use these hazards to identify specific requirements on artifacts that we will produce as part of the collected evidence. So I mentioned confidence. We also, in the QGen structured arguments, have a part of the argument that focuses on confidence in the demonstration. While we're using the overarching properties as the basis for our qualification, we're also reusing many of the expected and integral processes that are common in traditional DO-based qualification and certification activities. These processes work well, they're well understood, and they're commonly accepted. From our perspective, there's no benefit in not applying these common integral processes. And indeed, the overarching properties do not require that everything be new. We can still conduct these integral processes and bring evidence of their completion, that we've satisfied their objectives into the arguments. And we do that through this confidence part of the argument. So we situate these processes in the structured arguments, and we say that by adhering to these processes, we provide confidence in our demonstration of fitness per use. So we've now looked at this complete overview of the QGen structured arguments. And this is the content of what we're building to support our qualification. What I'd like to do now is talk briefly about the mechanics of how we're recording the argument. So for the qualification of QGen, we're using ViewRTO to capture all of our qualification artifacts, and this includes the structured argument. Each element of the structured argument is individually stored in ViewRTO as a first-class artifact. So each premise, each reasoning, each backing, each defeater, all of these are individually captured in ViewRTO, along with the parent-child relationships that assemble these individual argument elements into atomic arguments. ViewRTO brings us a lot of benefits in capturing the argument in this way. We're able to link argument elements to artifacts that are serving the role of evidence in the qualification of QGen, and we can identify the explicit dependency of an argument element on those artifacts. This means that if an artifact changes, we can be notified of the change through impact analysis, and we can come back and re-examine that part of the argument to see if it needs to be updated. We can also capture formally the review of the arguments, and we can capture the state of that review in ViewRTO and communicate that with our auditors. Finally, ViewRTO gives us configuration management and version control over the complete argument. Now, I mentioned earlier that we have two views of the argument, a textual view and a tree-like view. Both of these views are actually produced as reports that are run against ViewRTO. So starting from the representation of the argument inside ViewRTO, we can then extract these two views, the textual and tree view, by running reports. This is very powerful, and it means that if an auditor wants to see the argument presented in a new way, they can ask us to do that, and we can create a new kind of report based on what's captured in ViewRTO. So that's how we're mechanically capturing the structured argument. Okay, so let me wrap up. AdaCore feels that the overarching properties and their assurance case really seek a more appropriate set of activities to provide confidence in critical systems and software. In particular for tools, we think that the flexibility that's provided here is very powerful and very appealing. So we're using and adapting the overarching properties for the TQL1 qualification of QGen. As part of this process, we build an assurance case for QGen that begins with a structured argument. We provide an explicit risk assessment that stands in for the assumed systems level safety assessment that's called for by the overarching properties. We situate common and expected integral processes as confidence in our structured arguments, and we store the structured argument in ViewRTO, taking advantage of configuration management, review, and audit support. This qualification activity is still in progress. We're working with our launch customer and their DERs, and we're targeting qualification for QGen later this year. Thank you very much for attending. If you have any questions, please don't hesitate to reach out in the chat or to reach out to me via email.